Can you hear me? It's a thumbs up. Okay, that's great. Yeah, thank you. Perfect. Well, good afternoon, everyone. You are currently attending a special edition of CRADLE Talks. This is the first of a two-part webinar series on space robotics, with the second session taking place next week. My name is Paul Benique, and I'm the Technical Project Manager of CRADLE, and I work at the University of Manchester Center for Robotics and AI. So you might ask, what is CRADLE Talks? It is a series of seminars and discussions highlighting the research and case studies from CRADLE, the Center for Robotic Autonomy in Demanding and Long-Lasting Environments, which is an EPSRC prosperity partnership between the University of Manchester and Amentum. But to stay updated on the latest CRADLE activities, please sign up for our mailing list at cradlerobotics.co.uk or follow us on our social media platforms via our handle cradle_robotics_AI. Right. So now it's my pleasure to introduce our resource speaker for today. We have Dr. Chris Brunskill, who recently joined Amentum as a principal consultant for space. So Dr. Brunskill holds a Master of Engineering in Electronics and Satellite Engineering from the University of Surrey and a PhD in Space Robotics from the Surrey Space Center. He completed his PhD on micro rover Terra Mechanics and participated in the precursor Lunar Robotics Challenge organized by the European Space Agency in 2008. His other experiences include
You're muted.
all right, that's all right. Thank you. Can you hear me now? I guess, yeah. Thank you.
Yeah.
Great, perfect. Right. So just to continue, his other experiences include leading the development of a program of CubeSat in-orbit demonstration missions, as well as managing innovative missions for last mile delivery and responsive hosted payloads focused on in-space computing and AI. Right. So without further ado, please join me in welcoming Dr. Chris Brunskill. Put the spotlight on you now. Go.
Thanks, thanks, Paul. Hopefully, everybody can hear me.
Yeah.
Yes, we can hear. Yep.
And if I do this, hopefully you can see some slides. All good. Okay,
Yes.
great. Okay, so thanks very much for the introduction. That makes the start of this very straightforward. It's a pleasure to be here today, and thank you for the invitation to speak. So what I'm going to cover today is two main areas. One just looking at the general concept of robotics and autonomy and infrastructure in space, and then a pretty wide-ranging sort of highlights reel of various projects that I've been involved with that touch on the technologies needed to enable robotics and autonomy in this sort of new in-space infrastructure that we see coming today. And some of this goes back quite far, but the same underlying principles still apply today. So it's quite interesting to have the opportunity to reflect on where some of the core technologies that enable the state of the art are still common to missions that have been around for some time, or concepts that have been around for some time. So just to jump straight in, I mean, when we talk about robotics and autonomy, what does that mean with respect to space? So historically, you're probably familiar with a number of the applications here. We think of planetary rovers, planetary landers that might have a robotic arm. Slightly more recently, we now have planetary helicopters, and indeed deep space probes, which, while they don't necessarily have actuated manipulators, could be considered autonomous systems where they are constrained by either their communications latency or the bandwidth. And really that applies in all cases here. And that's driven the need for these systems to perform operations based on decisions that they're making themselves. That's where the autonomy comes in. The typical kind of applications you might see from the autonomy side is SLAMs, simultaneous localization and mapping, and autonomous path planning. So we give rovers an objective target to reach, and it then has to manage its own path planning and avoid obstacles. Trajectory planning for the robotic manipulators as well. All fairly typical for these kinds of applications, but having to perform those operationally in a very extreme environment of either a planetary surface or deep space. So the point here, concept of robotics and autonomy, not necessarily a new one in the space environment. Similarly, with in-space infrastructure, so the title here talks about the future of infrastructure, but in-space infrastructure is by no means a new concept. We have extensive capability and equipment in situ across all Earth orbits, low Earth orbit, medium Earth orbit, and geostationary orbit, and indeed in the lunar environment, other planetary environments, and in deep space as well. And some of this equipment is extremely substantial. The image here shows the Viasat 3 platforms in the Boeing clean room, ready for final integration and launch. And indeed, the second Viasat 3 is on the pad today. That will launch, I believe, later this evening. And you can see that this is an extremely comprehensive piece of space infrastructure. So Viasat 3 gives 1 terabit per second of bandwidth per platform. The constellation has multiples of these platforms. The solar arrays, which you can see stowed here when deployed, can generate at least 25 kilowatts of power. And these spacecraft each have a mass of 6 tons. So we're talking about effectively extremely comprehensive infrastructure that's already in space. But there is a change. There's an emergent need, and it's driven by a couple of broad areas. Firstly, building bigger infrastructure in space. The interest in space, the need for space, and the economic and strategic importance of space is demanding more and more capacity for our existing infrastructure. But the vast majority of our space systems are indeed deployed as single units, and that's limited by our launch vehicles. So just to give some numbers to that, the largest launch vehicle, on paper at least, today is the NASA SLS. That'll take about 95 tons to LEO and has a volume of about 14 cubic meters. The ISS is the largest piece of space infrastructure that we've, as humanity, have ever deployed and assembled in orbit. That has at least 400 tons of mass and a pressurized volume of 900 cubic meters. So we're looking at tens, if not more, of launches to replace something like the ISS at that scale. How do we do it? Well, modular systems, robotics, in-space assembly, all allow us to assemble this type of infrastructure in pieces on orbit. But the ISS in this example was heavily dependent on astronauts as part of that assembly process. So the robotics and the autonomy was certainly present, but somewhat limited in its application. Looking into the future, larger or future space stations, larger space stations, planetary bases, so the lunar village as a concept, and other extremely large-scale structures are going to be necessarily dependent on robotics and autonomous systems to support their deployment. And those systems can take advantage of the technologies available today, the advances that allow more independent operation and the high performance that comes with them. We're also seeing a change in the commercialization of space in general, so not just large individual structures, but certainly in a more practical sense today, the upmass being delivered to space is increasing exponentially and has done over the last 10 or 15 years, largely enabled by the easier access to launch. Booking and deploying spacecraft in orbit is much more straightforward than it was only a few years ago, and indeed the commoditization of technology that allows space systems to be produced en masse. There are various examples of this, Starlink being an obvious one, which is representative of a large proportion of that growth over the last few years. But for Starlink as a baseline, we see various other mega constellations either being deployed or being planned. And indeed, the general growth of the commercial space market, where having a space asset or a collection of space assets becomes another line on your capital sheet, rather than an exceptional piece of equipment that you might not consider otherwise. But what does this mean? Well, we need to now manage that equipment. We need to manage the environment that's being deployed into, which has created the growth of the need for ISAM, in orbit servicing, assembly, and manufacturing infrastructure. So this is the infrastructure that supports the infrastructure. And we see that robotics and autonomy are now finding new applications that enable these services, the logistics, moving equipment around, but also the servicing, assembly, repair, and in future reuse as well. We have some great examples here of missions, ISAM missions, that is, that have happened today. So Astroscale's Address-J mission is a great example of in-orbit inspection, where they've approached a spent upper stage, which was launched by the Japanese several years ago. It's now defunct and tumbling in space. The Address-J mission was able to approach that and maneuver around it to capture a very high quality imagery of all aspects of that target object for potential future management or disposal. And we also see the same application, same concepts in GEO, with the Space Logistics and Intelsat Mission Extension Vehicle mission. And this is a fantastic example of a rendezvous and docking application. The image here shows the view from the servicer itself. So you can see in the corners, these are the sensors and the robotic interfaces that then will capture the target spacecraft in the center here. The circular structure in the middle is the launch adapter, and that's the main physical interface that the servicer will integrate into, and then take over the attitude and orbital control of that platform and maintain its position in terms of station keeping, and indeed reposition it as needs be. So there's been several successful missions in this demonstrating this concept, and indeed providing it as a commercial capability. And again, this is a fantastic image from GEO. You can see the Earth in the background there as well. So extremely successful missions. So I'm just going to play a quick video if I can get this to work. There we go. So I was thinking I could put a big graphic together for this, but actually ESA recently provided this very helpful video that gives a great concept for what the future of in-space infrastructure might look like. And the difference here is that we see this persistent and continuous presence of things like cislunar platforms, lunar orbital stations, lunar constellations, transportation to deeper space locations like Mars, and orbital transportation around Earth as well. Fundamentally, this is around, again, the point of having increased upmass availability. So this is an ESA reusable spacecraft concept. You can see there's modularity there in the propulsion system that allows for easy refurbishment, repair, and reuse. We're recovering that second stage back on the ground. Might look quite familiar as a concept. I think the best approach to this was probably solved quite some years ago, and we see very similar approaches from other suppliers and developers around the world. But the business end here is the payload, and we can see a cluster of customer equipment that's being deployed. Again, in principle, recovering that second stage for reuse to increase the cadence of mass deployed to orbit from the Earth's surface. We then have the persistent capability, space tugs, orbital transfer vehicles. We'll talk a bit more about those in a minute, which are capable of then rendezvousing with that payload, that cargo, capturing it, and then maneuvering it to a new position in space, whether that's another Earth-centric orbit or indeed towards deep space location. In this example, we see the Odyssey refueling outpost. To establish this, we will need to provide in-space assembly and systems to integrate that in deep space. And then it provides that baseline infrastructure itself. So here is our tug docking with the outpost, the Odyssey outpost, and refueling itself. So this can continue to be reused over an extended period of time. Similarly, it can provide logistics services for more high capacity payloads, such as the lander that's illustrated here. And when we bring that all together, what we see is this comprehensive future infrastructure that goes beyond some single-use ad hoc, wholly integrated systems into an ecosystem of services and capabilities. And really what that reflects is an emergent space economy, in-space economy, where we're not just providing value back down to the terrestrial end user, but the value is transactional in space and only in space. So that's where we believe we are going. So that's the kind of background of the concept. This is what we mean when we talk about space infrastructure. I'm going to jump into now some examples of some of the technologies and the technology challenges that will enable this future view. So Paul mentioned that the Space Resources Challenge that was recently expertly executed by the CRADLE team is not the first time that ESO have addressed this challenge. Crater exploration back in 2008 was a big topic. Back in 2008, we were looking at things like the Martian, the NASA Mars exploration rovers, the Curiosity rover being the state of the art, Curiosity being under development, the Rosalind Franklin, then the ExoMars rover also under development, and the MERs having recently been deployed on the Martian surface. And one of the big challenges was not only maneuvering around on the loose dust and regolith on the Martian surface, but also traversing into and out of craters. And the lunar angle on this is back in 2008, we were only just realizing how prevalent water and water ice was on the lunar surface. So the application of robotics to be able to descend a crater surface into a permanently shaded area, collect samples for further analysis, and return them to a base station back outside the crater rim was conceived into the concept that became the 2008 Lunar Robotics Challenge. Other than the crater traversal of up to 40 degrees, the other requirements were fairly comparable to the recent Space Resources Challenge. So for the purposes of this field trial, we had a weight limit of 100 kilograms, a power limit of about 2 kilowatts, and the volume was constrained to half a cubic meter. And as this proceeded, or the development of the lunar facility, we were in the field literally on Mount Teide in Tenerife at about 2,000 meters elevation, where we had a terrain that was considered representative of what might be found on the lunar or the Martian surface. Now, why was this important? The big challenge with robotic rovers, and certainly small robotic rovers, is the tractive ability. So that is their capacity to develop forward thrust, maneuvering around on loose sand and regolith. Again, we'll have seen that in the lunar facility, where the wheels slip and trying to traverse any kind of slope becomes increasingly challenging. So when we look at small rovers, we can start to apply the concept of terra mechanics, which is a methodology that allows the drawbar pull, the net force, to be modeled and predicted, and then we can start to do comparisons and trade-offs between things like tracks and wheels. It's quite hard to see on these small plots, but the tracks there are developing roughly twice the driving thrust of wheels. However, for a track to work, we need to consider things like grousers, decoupling those grousers from the links or the belt that forms the rover track itself. And in that, you've got multiple components, multiple parts, multiple points of failure that might not justify the additional thrust that is produced by a track. It also turns out that modeling the performance of these systems is quite challenging, and the behavior of the regolith is not straightforward when it starts to be applied in the conditions that we might find on the lunar or the Martian surface. So back to the LRC, taking all of this into consideration, we came up with a concept based on a mobile robots Pioneer 3AT. So this was a state-of-the-art R&D platform at the time, and we completely refurbished that and refit that with an upgraded mobility system based on four-tracked actuator or four-tracked systems. These were actuatable in order to fit that volume constraint. It also provided us with a level of active suspension And again, you can see we've integrated here a navigation camera. This is for 3D SLAM applications, providing the imaging capability, but then also the onboard processing that can produce the maps, and a very straightforward 6-degree of freedom arm to collect small samples. For this challenge, I think we had to collect only a few hundred grams. The principle was the collection and retrieval at the crater wall, not the quantity of material as was defined for the beneficiation concept. So at the base here, we can see a couple of examples of the rover in situ in Tenerife. I should also say to reflect the lunar conditions, this was also done at night time, and I can tell you the 2,000 meters on Mount Teide in October, it's pretty cold and wet, even if you're on Tenerife. So the outcome of this, I should say, unfortunately, we had some mechanical issues that didn't allow us to complete a full run in Tenerife, but the principles that were observed as part of the development work here did go on to form the basis of my PhD research. So that's planetary robots. Moving to a completely different area is in-space logistics. And this is another interesting area in that the commoditization of technology has allowed for orbital transfer vehicles to be produced at a cost that allows them to add significant value to other smaller spacecraft that need to be maneuvered in space. So, for example, if you are part of a SpaceX transporter launch, the deployment of your spacecraft is actually quite limited in where it can be positioned in the orbital environment, and particularly when you've got a smaller platform, you wouldn't have substantial propulsion. So the concept of an orbital transfer vehicle addresses that. In one application is last mile transport, providing that orbit reconfiguration that allows your spacecraft to enter its operational orbit, or a more optimal operational orbit, in a way that it wouldn't otherwise have been capable of doing so. But also looking further ahead, the concept of an OTV can also be considered in the same way as you might consider a drone on the Earth's surface today, or in the air on Earth. And of course, drones have many different applications beyond just transportation. So the concept of an OTV is fundamental to the future of large-scale in-space infrastructure. And just really to hammer in that point on the value of being able to provide the last-mile transportation, here's an example of one of the very early ION missions performed by Deorbit. On the left there, you see a number of Planet Labs, as they were called then, Planet Now, doves. So these are CubeSats. In blue, there are those that were deployed directly from the SpaceX transporter launch vehicle. And what we see is that there is a clumping together. These would have been deployed sequentially at the same time, possibly in 2 or 3 batches, as we can see here. And the issue is that these are now overlapping in their image capture range, right? They're Earth observing spacecraft, and we have large gaps in coverage, which is gaps in time that aren't able to be caught or captured by the spacecraft. What Planet typically do for the doves is to use differential drag, literally flying into the wind, and they'll position the solar arrays into the velocity vector, and the tenuous atmosphere at that altitude does bring the altitude down slightly, and therefore through orbital mechanics adjust the velocity and allows them to spread out somewhat. However, on the right, we see the doves that were deployed by the ION platform sequentially, and it's evident here that we have a very even spacing of spacecraft. And the economic case here is that those spacecraft now are producing revenue-generating imagery in a timescale much shorter than the typical ConOps used up to that point. Sort of slightly aside here, but also under the very broad umbrella of autonomy is cloud computing in space. And the reason this is relevant is that once you've got OTVs and persistent and continuous infrastructure in space, you can start to use it for other things. Hosted payloads and hosted payloads as a service is now a very common capability that can be procured pretty straightforwardly from various different suppliers across the world. And the reason why cloud computing is of interest to the space community is initially in the processing of the large quantities of data that we generate in space. Arguably, we produce more data in space today than we could ever possibly downlink to the ground. So we either have to throw that away or get down as much as possible to process on the ground in order to determine what elements of the data sets are useful. So an image of a clear sunny day is very useful. An image of a cloud is less useful depending on your mission application. And equally, we've also seen emergent technologies in advanced onboard processing, edge computing, and looking into the future a little bit, centralized orbital data centers as concepts that are starting to be demonstrated. And there are some examples there of companies doing that today. Lone Star landed a data store on the moon through a private launch lander operator, Intuitive Machines. StarCloud yesterday launched their first orbital data center, small demonstrator on the Bandwagon mission, and Planet have edge compute built into their most recent Earth imaging spacecraft, which is based on NVIDIA Jetson onboard processors. And of course, Deorbit have the cloud services through their hosted payload service as well, which is something that exists today. So we looked at that concept of hosted payloads and demonstrated some early cloud compute and edge compute capabilities. And the real sort of important takeaway from this is that with this infrastructure, the mission was never designed to have any kind of or specific application or software deployed or executed on the platform before launch. So the ION spacecraft was built, launched, it hosted the Unibap IX5, which is a small onboard processor with a very generic compute capability. So it's got an x86 based processor. It's got some co-processors for graphic and AI acceleration. But otherwise, it's a fairly typical compute platform. ESA ran an interesting call for ideas to explore the use of in-space processing for cognitive cloud applications. And through this, we're able to demonstrate 5 applications on this hardware that was already in flight. And we completed that in just 6 months from discovering that the applications themselves, engaging with those end users, helping them port the software into the hooks that were required for this platform from Unibap, and then uplink, execute, and retrieve the results. Very, very short turnaround with no access to the hardware on the ground other than an emulator for the processor. We also demonstrated with Amazon an extension of the AWS IoT Greengrass edge services. So don't really have time to go into depth on that, but it was an extremely interesting project where essentially we were able to extend the AWS cloud into the orbital environment by integrating IP over RF links between the IX5 on the ION platform and the AWS data center on the ground, and then start to perform very typical compute services, microservices, producing image sizes, performing some kind of machine learning type processing as well. So again, in-space infrastructure providing autonomous capabilities for the future of future applications, future missions. So back to the space environment, the infrastructure itself. How do we move around? This is an extremely challenging area. The ability for a spacecraft to know where it is, know how it's moving, know where its targets are, and maneuver around those safely is one of the largest technology hurdles that we have to cross in order to enable a lot of the fundamentals of the future of in-space infrastructure. So this piece of work looked at a fairly typical GNC loop. So we have the navigation stage with the sensors, which then feed into a filter to update the state. The guidance loop here then provides some trajectory planning, and then we have the control aspect to perform the maneuver as required. And the concept here was to perform a close proximity autonomous inspection of a solar sail spacecraft. And to do that, we used a couple of really interesting novel technologies. So in the guidance or the control loop, we have a microchemical propulsion system, which I'll talk about briefly, but not really the core. But more interestingly for me was the use of a visual inspection payload concept, which used very basic cameras and some advanced algorithms to perform relative position and pose estimation. So the microchemical propulsion system, you can see here on a 1-cent coin, it's essentially a MEMS microthruster. It's based on hydrazine, which is a monopropellant, and the catalyst bed was etched into the silicon itself and coated with the catalyst or the catalytic material. And this was used conceptually to define all of the basic maneuvers needed for rendezvous and orbital motion, and also maintenance of the orbit itself. But the visual inspection payload was the real sort of core of the GNC novelty. This is a really clever algorithm, not one that I developed, but one that I implemented in an experiment, which allows the target object to be bound in a spheroidal volume. And then when that is projected onto a 2D image plane, you get an ellipsoid. And this algorithm then allows you to reconstruct the original spheroid position and pose based on its projection onto that 2D image plane. So to demonstrate that, I 3D printed some spheroids of different shapes and sizes, representative of different target objects, captured those using an imaging system, and then developed some algorithms to define that bounding ellipsoid, and then process it into our projection of the or reconstruction of the spheroid in 3D space relative to that image plane. And what you can see here is the black is the target object, the truth model. The red is one of two solutions, and the yellow is a second solution, because there are two projections which create a single ellipse. And in practice, you would then be able to filter out the incorrect solution over multiple frames, because you would get a larger discrepancy as you go. But again, really clever capability that used fairly straightforward rudimentary technology to produce a very capable capability, a very high capability to perform navigation autonomously with target objects of arbitrary dimensions. And just back on that, a lot of algorithms today try and do sort of shape fitting and model fitting to CAD models, sort of pre-known information that's uploaded to a target, a servicing platform, and then it'll take multiple images, or maybe use LiDAR or a 3D type camera. This is completely independent of all of those capabilities. All you need to do is know the dimensions of your notional spheroid, and you can reconstruct position and pose. So on the ground, we can also validate some of the relative motion needed to perform close proximity operations for in-orbit servicing and assembly. We can use surface tables. So this is the surface table at the University of Surrey. It's about 3 meters by 2 meters in dimension, and the surface is of a metrological standard. That is to say, it's smoothed within a few microns across the whole surface. And you can maneuver around that using essentially a reverse air hockey table concept. These are floating platforms with compressed air, and then the pucks underneath that allow you to maneuver around. And by tracking the position of these and providing some thrust using air jets, you can replicate the motion on orbital motion in the lab to validate control algorithms. For those of you from Amentum and indeed CRADLE, you'll recognize the gravity offload system. So very similar principle. This is a much more recent piece of equipment that we developed for the satellite applications catapult ISAM yard in Westcott. And what we're looking at here is the rig that suspends a displacement gantry, and suspended from that gantry is this barrel-shaped target, which represents your client spacecraft. As your robotic arm representing the servicer is maneuvers along this rail closer to the target, you can emulate the orbital motion, and then sensors on board the system itself measure any impact or disturbances from that client servicing spacecraft, and can offset the target in a way that is representative of how it maneuver in a microgravity environment. So a very, very different approach, but essentially the same thing. It's emulating that motion in space. Motion in space, again, not much time to go into that, but very non-intuitive, and quickly gets into the sort of catastrophic region if we don't manage that very, very carefully. And then just to finish off, looking a bit more to the future, ESA also recently ran a circular economy study looking at the future of future needs or future mission concepts to meet their net zero by 2050 target. And the scope of this was looking at reuse, refurbishment, and repair of future spacecraft to extend their life beyond their original design specifications. So in this example, we looked at the concept of refurbishing a geostationary satellite. The ConOps was to launch a demonstrator. So this is a technology demonstrator representative of a geostationary platform and a client, and a servicer as a single unit. Maneuver that into the geo region, then undock and perform a refurbishment mission. And in this instance, it was using a robotic manipulator to replace a PPU, a power processing unit, which is a fundamental aspect of the electric propulsion system used on many geostationary satellites. So again, the concept here is that with modularization and robotics, and indeed the autonomy needed for the GNC, we can approach and either dock with or reconfigure target and client spacecraft to replenish consumable equipment. A PPU has a design lifetime of maybe 10 years, whereas the remainder of the platform could last much longer. And by replacing that, the life can be extended, and then the platform operated as designed for an extended period of time. It also opens up other interesting concepts where you could have a single satellite repair kit. So your robotic system, as shown in the servicer, with a set of spare parts, if you like, that are then at the disposal, as it were, of multiple geostationary platforms. We don't know if a system is going to fail. There's a percentage chance that it can. It could be redeveloped for a shorter lifespan, and on the basis that it is replaced on failure. But we don't necessarily, from a statistical performance perspective, need to replace all of them all the time. We can be responsive to failures as they happen by having, again, a persistent and continuous presence in the orbital environment. It also helps with the economics of in-orbit servicing, where you can have a single unit that can be at the disposal of multiple clients by design. So just to close and look to the future, I think the main sort of takeaway messages here is that infrastructure in space, it's not new, but it's going to continue to grow. And even though we have quite extensive infrastructure at the moment, the scale is only going to become larger. Private space stations, space-based solar power, orbital data centers, permanent lunar bases, in-space resource utilization are all concepts being worked on today and deployed today. These will happen at some point in the next 5, 10, 20 years, and there is fundamental need for new technologies to support the deployment, management, operations, and disposal of all of these pieces of equipment. The infrastructure needed to deploy that is also going to need to grow with it. The Starship being produced by tested by SpaceX now. I'm sure everybody's familiar with this. It's going to be a step change, orders of magnitude growth in upmass. And again, ISAM services are going to continue to need to be more sophisticated and prevalent to support this growing area. We need better regulation and standards. We need to be able to qualify this equipment to ensure the safety and sustainability of the space environment. And just as the final parting note, we always need better hardware, better software, better equipment, better robotics, better algorithms. So there's plenty of really interesting engineering still to do in this area. So with that, I'll stop. Thank you very much for your attention. I'm very happy to take any questions.
Okay, thank you so much, Chris. That was really interesting. We are now opening the call for questions. Please raise your hand or type in your questions on the chat if you have any questions. While people are still thinking about their questions, I have my first one, if that's okay. So you have first experience of both the Lunar Space Research Challenge and the ESA Space Research Challenge. Is there any difference in terms of technologies from both the participants and the organizers that you've noticed since between the two challenges?
Yeah, I think there's a couple of interesting observations, I guess. One is simply the quality of off-the-shelf equipment is much higher now than it was back in 2008. And I think certainly in the moles concept, I saw a very capable, comprehensive system integrated in very short order of time. Part of the challenge we had with our rover was we had to take the angle grinder to it quite a few times to reconfigure it for that design, because it simply wasn't intended for that kind of use. It's sort of lab-based, pretty straightforward application. So I mean, maybe on the grass was at most. I think the other area is sort of the expansion in scope of the mission concept as well, from the organization perspective. As I said, the sample quantity was a few hundred grams, fairly sort of nominal in terms of our objectives. Whereas for the beneficiation objective, we're talking multiple kilos, which is by definition orders of magnitude more material, and again sort of requires a much more robust and higher sort of not quality but much more substantial engineering solutions in order to meet that mission objective, which again probably wouldn't have been quite so feasible in the timescales that we had back in 2008.
Well, we have questions now. So we have one from Pavel. So thanks, Pavel. Thanks for the presentation. When it comes to the orbital docking, what would you say is the biggest challenge?
So there's a number of challenges. I think we can touch on a number of areas. So firstly, standardization is a sort of fairly practical element. Understanding the performance and the quality of those interfaces and how they can be integrated without having to develop new interface systems on a case-by-case basis is a step change that we need. And there's work that is and has been done in that area quite recently. I think one of the big challenges with that is that we take quite a typical space approach to it, and we've ended up with some quite over-engineered solutions. So finding that balance of an interface that is practical but not unreliable, but not over-engineered is one of those. The ability to control your spacecraft after docking is again more of a commercial challenge, actually, in that without fairly detailed engineering information about your client spacecraft, tuning your control algorithms to be able to manipulate or even just hold a steady station keeping position can be quite challenging when you're performing the servicing logistics as well. Yeah, I mean, there's lots of challenges. There's a couple of that jump straight to mind.
Okay, let's move on to the next question. So from Federico, could you discuss about how much the tasks carried out in space with robots are via teleoperation versus autonomous? And among the autonomous ones, what's the degree of autonomy?
So this goes back to the ISS example where the robotic arms are fundamentally operated by astronauts using joysticks on the ISS. So from an in-space assembly perspective, the precedent is for teleoperation. But obviously there's a challenge there in that you need a human in space in close proximity to the robot to be able to do that. There had been some examples of teleoperation, in fact, from the ISS to the ground. So I think it was Tim Peake actually that showed the one of the ExoMars rover demo or engineering platforms being operated from the ISS. The Russians operated their lunar rover from the Earth's surface directly back in the 60s. But I think the point here is that autonomy and the capacity for autonomy, both in terms of the sophistication of the algorithms, but also the compute capability, makes it much more accessible to deploy that capability on board, and the sort of standard benefits of robotics then start to come into place, where you can tune and develop application-specific solutions that are very optimal for certain tasks over and over again. That's not to say we won't have more generic robots and humanoid robots, but there's an opportunity there to optimize the tasks at hand.
Thank you. And we also have a question from Dave. Really great presentation. Do you see a potential for multi-agent robotics? And if so, what do you see as their most important use case?
So I think there's a couple of really great examples of where that could be used. The obvious one is swarm robotics on planetary surfaces for mapping and exploration, prospecting, and so on. There's potentially a sustainability question there in terms of deploying large quantities of perhaps semi-disposable units. It needs to be managed as well. But going back to the in-space logistics, formation flying and cooperative operations between spacecraft is an emergent area. The concept you might see today is a cooperative docking maneuver, but if you've got large numbers of logistics platforms, OTVs, that perhaps need to maneuver a payload or a client piece of equipment optimally between orbits, potentially you could have a sort of a mesh capability of OTVs across various orbits that can then hand off at certain points. And indeed configure themselves to optimize for the coverage needed for any kind of remote sensing or prospecting and inspection and so on. So I think cooperative robotics, cooperative platforms is a very interesting area that can there's a lot of scope for future work.
Great. Thank you. Do we have any other questions from the chat, from the audience? I think that's all of it. But in any case, thank you so much, Chris. I think that's all the time that we have as well. But thank you so much, Chris, for lending your time with us, and thanks everyone for attending this webinar series. I think there's more things. Let me just check. Nope. Okay, yeah. So in any case, next week, we will hear from Team CRADLE Talks, who recently participated in the second Space Resources Challenge. And This is organized by the ESA European Space Agency and the European Space Resources Innovation Center. So this will be a hybrid event, meaning apart from attending online, you can also join us at the University of Manchester in person in the Odd Fellows Hall, room G007. So details are in the description. So again, thank you, Chris, for your time, and thanks everyone for attending. I wish you all a great day. Thank you.
Thank you. Bye.
Thank you.